Last class, we started learning about gases. We're going to continue learning about gases today. Does anyone remember any of the three gases that we learned last time? Gas laws.
The Charles law.
Charles' law, Charles in charge. Boyle's law.
Charles Boyle's.
Nope, not Charles Boyle's law. You've got the right idea. It is the combined gas law. I was hopeful that we'd be able to get that one since it is on the screen. So, combined gas law is a combination of Boyle's law and Charles' law. Boyle's law is P1 V1 equals P2 V2. Charles' law V1 over T1 equals V2 over T2. And if you combine them, then you get the combined gas law. Ta-da! And remember that when we're doing anything with gases, our temperature has to be in kelvins. This is somewhat important. So how do we use the combined gas law? It looks something like this. A sample of a gas has an initial volume of 241 milliliters at a pressure of 755 mHg and a temperature of 32 degrees Celsius. The gas is compressed to a volume of 115 milliliters and heated to a temperature of 94 degrees Celsius. What is its final pressure in millimeters of mercury? So we got a whole lot of stuff that was provided to us. And one thing that we're looking for final pressure, specifically in units of millimeters of mercury. One nice thing about the simple gas laws is that we can sort of use whatever units we want to going in. I say sort of because it depends on what the problem's asking. So in this case, it's asking specifically for millimeters of mercury for the pressure. So we need to make sure our final answer is in millimeters of mercury. And also because we can't use degrees Celsius, because that'll screw everything up. A great place to start for all of our gas law problems is to list out everything that we were given, which in this case is lots. So our initial volume at a pressure, meaning these two things are connected, and a temperature, the and meaning these are also connected. That means that these are all our initial states. So we're probably going to guessing that you'll give them the 1 instead of the 2. It doesn't matter. You can give them the 2 instead of the 1. The important part here is that we get these all together. And we need to convert our degrees Celsius, so we add 273 and some change. And then we've got our state 2 variables, V2, T2, and we are solving for P2. Strictly speaking, you don't have to write all the variables out again, but if you're not great at keeping track, or if you're just not quite sure that you're good at keeping track of variables yet, I would recommend just go ahead and write them all out. The little bit of time and effort that you spend writing them out could save you points and headache, both important things to minimize, or sorry, to optimize. You want to minimize headache and maximize points. So P1 V1 over T1 equals P2 V2 over T2. We want to get P2 by itself. So we're going to multiply by T2 over V2 to get them to move from the right side to the left side. Now we no longer have a question mark. We've got T2 over V2, P1, V1 over T1. For any of the simple gas laws, you want to make sure that you've got the thing you're looking for on the top, and everything else should have another variable, one on the top, one on the bottom, one on the top, one on the bottom, so that the units all cancel away. And then we get to put all of these lovely numbers in. And you want to make sure that you put the correct ones in. V2, T1. Should look something like that. And then our Kelvin cancel, our milliliters cancel. We're left with the unit we wanted, millimeters of mercury. So then we get to multiply everything on the top and divide by everything on the bottom. It might be a good idea, might be helpful if you're putting this all in at once, parentheses around what's on the bottom, or you can multiply everything on the top, get an answer, divide that by what you get when you multiply everything on the bottom. And our pressure is 1,900 millimeters mercury with 3 significant figures, so we get to put it in scientific notation. Any questions? Our 3 simple gas laws so far: Boyle's law, Charles' law, combined gas law. We've got more simple gas laws. The next one that we are learning about is Avogadro's law. What else do we remember Avogadro for?
His number.
His number. What's his number related to? Moles. His number is related to moles. I thought it would be funny to bring in a mole. Not a live mole for those listening, unless you think that's cool, and then it is a live mole, and he's very well taken care of. But for everyone else, no, it's not a live mole, it's just a plushie. Okay, so Avogadro's law relates volume and moles. If the amount of gas changes, what happens to the volume? That's kind of all Avogadro's law is thinking about. As it turns out, the volume of a gas sample increases linearly or is directly proportional to the number of moles in the sample. More moles, more volume. And we'll talk about an instance where we probably have experienced this. This relationship is credited to Amedeo Avogadro, the guy that we know for his number, 6.022 times 10 to the 23, we'll say particles per mole, or pieces per mole, usually atoms, molecules, formula units, one of those 3. Avogadro's law states the volume of a gas and the amount of gas are directly proportional, so when volume goes up, number of moles also goes up. And this statement looks, or this equation, or law, looks pretty similar to Charles' law. We've got V on top and something else on the bottom. So if you want to memorize something for Avogadro's law, V over N is probably what you would want to memorize. Avogadro's law shows up in blowing a balloon. It also shows up sort of in inflating a tire if your tire is really flat. So as you blow up a balloon, you blow, this is you in the picture, you blow air into the balloon. What happens? The balloon gets bigger. You're adding more volume in. You're adding more moles of gas. You're adding air into the balloon, so it gets bigger. Pressure is constant because the pressure inside equals the pressure outside. That's why the balloon expands, so the volume gets bigger. and the temperature should be roughly the same. So you can try this one pretty safely at home. If you blow too much, though, the balloon will explode in your face, so don't do that. Unless that's something that you're trying to do, in which case, have fun. So Avogadro's law, V1 over N1 equals V2 over N2. And as a reminder, we don't necessarily have to memorize all of the simple gas laws. It doesn't hurt to memorize them, but we'll be learning a way later today that we can come up with them a little bit easier, and so we don't have to memorize them. But if you don't like algebra, it's not going to work for you. So our example for Avogadro's law, a balloon has been filled to a volume of 1.90 liters with 0.0920 moles of helium gas. So it floats. We can do the raising your voice trick. If 0.0210 moles of additional helium is added to the balloon while the temperature and pressure are held constant, meaning we can use Avogadro's law, what is the new volume of the balloon? So we've got a volume, we've got moles, we've got moles. So V, N, and N. Our volume is 1.90 liters. The first number of moles that we see is 0.0920 moles. The second one is 0.0210 moles. The 1.90 liters goes with which of our two moles? The first moles or the second moles? First moles. The with connects them. So 1.90 liters with this many moles. So we'll call those our V1 and our N1. What do we label our other N? We can label it N2. What do we expect to happen with our volume? Is our volume going to go up or is our volume going to go down? Okay, we've got two of the three reasonable options. Volume will go down, volume will go up. It seemed like people sort of settled on volume's probably going to go up. So let's see if that happens. We need to solve for V2. So we're going to multiply both sides by N2. That'll get it to move to the other side. We'll be left with something that looks like V2 equals V1 N2 over N1. We will plug in our numbers. And let's just write out our prediction. Prediction, volume goes up. Our N2 is 0.0210 moles. N1 is 0.0920 moles. The moles cancel. I'm leaving off the helium label because in our gas law stuff, because of the way kinetic molecular theory works, the identity of the gas doesn't matter. So we can leave it off. You can leave it on if you wanted to. So 1.9 times 0.021 divided by 0.092. The volume that we're predicting, 0.434 liters. Is that up or down? That's down. Why did we expect it to go up?
It's not because the law states that they're proportional. So if it goes down, at the end is down, then the V is going to be down.
That's true. If our number of moles goes down, then our volume should go down. Did our number of moles go down? Looking at the text of the problem. What does it say about the 0.021 moles? Of additional helium is added. So we're putting more gas in. That should be the reasoning behind why we expect the volume to go up. So what went wrong?
We didn't add the moles of helium added to.
Yeah, we didn't add this moles. We just used this. So in the way that we solved the problem, we took this moles initially. We completely emptied out the volume. We emptied out all the gas, and then we refilled it the way that we solved it. What the problem is asking for is we added this 0.021 moles to the initial amount that we had. So the balloon should have gotten bigger. So we need to, our N2 should actually be this number plus this other number. So this is one of the reasons why it can be helpful to make predictions before you start a problem. And or it can be helpful to think about, does my answer make sense once you've solved the problem? So with our new volume, our new moles, we should find a better, bigger V2. And that bigger, better volume is 2.33 liters, which is bigger than our initial volume. So that tracks. Questions? This might be a perfect example of why some people hate word problems. I like to put one tricky problem. I'm calling this a tricky problem. I like to put one tricky problem on the exam usually, so you can expect one surprise at least. All right, Avogadro's law exercise. So this is one that I'll give you to try. A reaction vessel with a movable piston is filled with 0.121 moles of reactant A and 0.5452 moles of reactant B. The initial volume is given. After the reaction is complete, the volume is here. How many moles are present in the reaction vessel at that point? So it's an Avogadro's law problem. We're going to need V1 over N1 equals V2 over N2. We've got some things that we are given. Some moles of reactant A, some moles of reactant B, and an initial volume. So we've got two N values, our volume of 1.53 liters. The question tells us that it's our initial, so let's give that the V1. After the reaction's complete, the volume of the vessel is that amount. The after in the sentence letting us know that's our V2. What are we looking for? We're looking for moles. Moles is an N value. We might be able to guess that we're looking for N2, but we already have two N values. If you're feeling like a kid again, it might be because of the tricks. If you're feeling like a rabbit, these tricks aren't for you. So the N values that we were given, moles A, moles B, we do have to combine those together. A plus B, that's all of the gas that we were starting with. So together, that's our entire number of moles. The identity of the gas is not important because we're working under somewhat ideal conditions. We're just going to add those together. So our N1 is the combination of those two. We're at the combination reactant A, reactant B, which is 0.573. And then we get to solve for N2. There's a critical mistake that you could make here. If you multiply both sides by V2 and then magically come out with N2 equals V2 V1 over N1, you've made a critical mistake. And that critical mistake is that N2, let's use a different color. N2 is on the bottom, and it needs to be on the top. So there's a helpful trick that we can do instead of making this error. What you can do instead, this is free, costs you no money, and hopefully costs you very little brain power as well. You can flip the top and the bottom for both sides. So now we've got N1 over V1 equals N2 over V2. We can do this because we're treating both sides equally, and so nobody's getting the short end of the straw. And now we can multiply by V2 on both sides to move V2 from the right side to the left side. And we get N2 equals V2 N1 over V1. And now we've got N on the top. So we're going to end up with units of N and a volume on the top, a volume on the bottom. Those should cancel out. Will cancel out. So 0.884 times 0.573 divided by 1.53. Our number of moles is 0.331 moles. We don't know what is in that 0.331 moles. It might be some secret third thing. We might have a little bit of A, we might have a little bit of B, we might have also 3 or 4 other things, who knows. The important thing is that that's how many moles we have. Questions about Avogadro's law? There are ways to do the other ones, the other simple laws in ways that are tricky. It's not just Avogadro's law that can be full of cereal. All right, that's enough simple gas laws. That's not all of the simple gas laws, but that's enough. So we are now going to learn the GOAT, the ideal gas law. You can combine Boyle's law, Charles' law, Avogadro's law, and the Gay-Lussac law all together. We didn't talk about the Gay-Lussac law. You can put them all together in one singular law, and that law is the ideal gas law. Why is the ideal gas law bolded? Yes, it's important. I would recommend memorizing the ideal gas law. Good to memorize. This is the form of the ideal gas law that I'd recommend memorizing. You can swap the variables around any way that you can algebra them. That's also the ideal gas law, as long as you didn't commit algebra fraud. And we've got pressure, volume, number of moles, and temperature. We've seen those all before. The new one, the new kid in town, is the R value. R is the ideal gas constant, and it's got this value. That's one of 2 values, I think, that shows up on our yellow sheet. There's a second R value. Secretly, there's many more. This is the one that we're typically going to use. This will be given when needed, i.e., next exam. So you don't have to memorize R. It wouldn't hurt to memorize R because then you just have it on recall. One thing that's nice about R, if you remember the units, is that it tells you what units you need. So there's some memory tools built into it. Our pressure has to be in atmospheres. Our volume has to be in liters. The amount of gas has to be in moles, and the temperature has to be in Kelvin. So the units you use must match the units in R. That's part of the reason why we can have multiple options for R. You can change the units in R. Typically, the pressure units are the ones that change. So you might also see liters, millimeters mercury per mole Kelvin, for example. The mole's typically not going to change. The liter's probably also not going to change. It's mostly just the pressure. So what's cool about the ideal gas law is that we can make our simple gas laws from the ideal gas law. The way that we do this is we're going to start with PV equals nRT. So you're always going to start PV equals nRT. And then you want to identify what variables are in your problem. So if your problem gives you two pressure values and a temperature value, for example, what we're going to do with our PV equals nRT, our ideal gas law, is we're going to get pressure and temperature on the same side. So to rearrange that, we're going to divide both sides. Let me rewrite it. We need P and T on the same side. Going to divide both sides by volume. Volume moves from the left side. We're also going to divide both sides by T. Let's do a lazy copy paste. We also divide by T. That moves the T from the right side to the left side. We end up with P over T equals NR over V. Then we just copy paste the side that has the variables that we want. And we get P1 T1 over P2 T2, which is Gay-Lussac's law. That's the simple gas law that we didn't learn. It also works for Boyle's law. It works for the combined gas law. It works for Avogadro's law. It works for Charles' law. It works for all of them. So if you don't want to memorize the simple gas laws and you feel like you can do this, or you might be able to learn this, this is a great way to come up with the simple gas laws. Otherwise, I would recommend making flashcards and studying so that you've got your simple gas laws memorized. What's cool about the ideal gas law is it's PV equals nRT. Notice that unlike Boyle's law, for example, PV equals PV, we only have one pressure, we only have one volume. So we don't need a second state, we just need one state, we need one set of conditions, and we can figure out what the other variables are, or what our missing variable is. That's what's neat about the ideal gas law. This also works like reasonably well for approximating under conditions that we're in, even though we're in non-ideal conditions. So we are looking for what? What is at the beginning of the sentence? That's our question word. And the thing that comes shortly after that is the volume. What is the volume? So we're looking for V. V equals question mark. That's going to tell us how to rearrange our ideal gas law. So divide both sides by P to move P from the left to the right. And you get V equals nRT over P. The other stuff we are given is the moles of a gas, the temperature, and the pressure. Unlike before, we don't have to set a state 1 or a state 2. We don't have to worry about any of that. Now we need to worry about what our units are more than we need to setting up 1 and 2. So N is moles, temperature 473 Kelvin, pressure 2.7 atmospheres. I would still recommend writing out all of your variables like I've done here, especially because a lot of the times the variables will need to get converted to some other units. That's not the case here, but it will happen in the future, I promise you. All right, so we are looking for volume. We've solved for volume. We have N, we have T, we have P, but we don't have R. Can we solve the problem? Where do we find a value for R? Kid named Yellow Sheet. Crazy thing to name a child. If you grab your yellow sheet, in the top right quadrant, you should see R. And there's 3 values for R. One of those we will not use in this class. 2 of them basically we're not going to use in this class. The R value that we're using here, 0.08206. On our sheet it says 5.8 instead of 6. Sometimes you'll also see it 0.0821, just different levels of rounding. And the units are liters, atmospheres per mole Kelvin. What we need to check at this point, before we plug stuff in, or maybe after we plug stuff in, it doesn't really matter, but we should check and make sure that our units are correct. So for our R value, we've got moles. For our N, we have moles. For our temperature, we have Kelvin. In our R value, we have Kelvin. We also have atmospheres in our R value. We have atmospheres given to us in pressure. All 3 of those match up, so that means that we are good to go. So the variables have units that match R. Time to solve. So V equals N, 0.453 moles, times R. Lots of us hate writing our units out. I'm among those. I don't like writing my units out. I always write my units out because this is one of the areas where I'm trying to be a good example. So we are going to write all of our units out. I encourage you to do the same. Because if you didn't check your units beforehand, when we go through to cross out our units to figure out what we've got left, we can catch ourselves if we're about to screw up with putting the wrong units in. I promise you that once you get used to writing out the units, it's not that bad. So there's our T, and we also have P on the bottom, 2.7 atmospheres. For canceling out our units, we've got moles. Moles is in the bottom of our units for R, so those cancel. We've got Kelvin. Kelvin's in the bottom of the units for R, so those cancel. We've got atmospheres on the top. We've got atmospheres on the bottom, so those also cancel. And what's left is liters. So volume equals something liters. So multiply everything on the top, divide by the thing on the bottom, and you should end up with your answer. That answer is 6.5 liters. We're rounding to 2 significant figures because of our 2.7 atmospheres. Questions, confusions, places we got lost, things we'd like me to say again? Cool. So that's like the easiest scenario for ideal gas law. because all the units work out. Let's do another easy one, but your turn. So we're using PV equals nRT. I didn't even say Siri, but okay. And we want an R value. So go ahead and solve for the pressure of the gas in our tire. Okay. We are given some numbers. We're given liters for the tire. We're given moles of the gas, and we're given temperature. So our volume is 8.5 liters. N is 0.55 moles. T is 306 Kelvin. In case that hasn't become obvious to you, if you don't know what PV, N, R, and T are in the ideal gas law, you can't solve the problem. Meaning, like, you have to know P's pressure, you have to identify what units of pressure are, you have to know V's volume, you have to know what units of volume are. N is always going to be number of moles, T is always going to be temperature. So make sure also when you're learning PV equals nRT that you actually know what PV, N, and T are, and that you can identify them in the problem. Otherwise, you cannot solve the problem, right? You'll just be hopelessly confused. And I'll see the question marks spawning repeatedly above your head during the exam, which is very distracting for me, by the way. We are looking for the pressure of the gas tire. The gas in the tire, rather. So finding P, there it is. We found P. We need to divide both sides by V. Pressure equals nRT over V. We've got all of these things. We've got our volume in liters. In R, we also have liters. We've got number of moles in moles. We've got number of moles in moles. We've got Kelvin for our temperature. We've got Kelvin in our R value as well. And then pressure is going to end up with units of atmospheres, because that's the one that we haven't talked about yet. Plugging our numbers in with all of our units. Oh, what fun it is to know units. Our R value has latem per molk for its units. And our temperature, 306, dividing by V, which is 8.5 liters. Lots of units cancel out, and we're left with atmospheres. We get 1.6 atmospheres, which is about 24 psi. So probably need to put a little bit more gas into our tire. For most of us, that's a flat. Questions? Shall we do one with unit conversions as well? I'm not feeling the enthusiasm for it, but we'll go ahead and do it anyway. Actually, no, we'll leave it as an exercise. I'll put it in the annotated slides, so you can check it there if you want to. That's the problem saying try me, not me telling you to try me. I'm not looking for confrontations in class. All right. Some stuff that we can do with the ideal gas law that's fun and cool to me, but maybe less fun and less cool to you, depending on how you feel about it, is we can use the ideal gas law plus mass measurements. I don't know why that says in with. Plus, in addition to mass measurements to calculate the molar mass of a gas. So we can calculate the molar mass of a gas rather than figuring it out from the periodic table based on what we know the chemical composition is. We can collect a sample of gas. We can take the mass of that gas sample. We can use all of the other variables in PV equals nRT to figure out the molar mass of the gas. Conveniently for us, we've got another problem with unit conversion. So we've got a sample of a gas. It's got a mass, that's M, of 38.8 mg, milligrams. It's got a volume of 224 milliliters. It's at a temperature of 55 degrees Celsius, and the pressure is 886 torr. What are the units for molar mass? Grams over moles. So sometimes we'll use capital M for molar mass, sometimes, and it's mass over moles, M over N. So if we have the mass, we do, and we divide it by the moles, which we can find because of the ideal gas law, that'll give us the molar mass. So we need to find the number of moles. We're going to be using the ideal gas law, PV equals nRT. The number of moles is N, so we need to find N. Move RT to the other side. And this will turn into N equals PV over RT. What's R, other than a pirate's favorite letter? Yeah, it's a constant. R, 0.08206 liters, atmospheres per mole Kelvin. Do we have liters? Nope, we've got milliliters. Do we have atmospheres? Nope, we've got torr. Do we have moles? No, we're finding that. Do we have Kelvin? Nope, we've got degrees Celsius. So we get to do a whole lot of unit conversions. What fun. For milliliters, select the correct tool. There are 1,000 milliliters in a liter. So 0.224 liters. For temperature, we add 273.15. We get 328.15. I believe in the past, I have not given the conversion between Celsius and Kelvin on this exam, which has been a point of frustration for people. I'm mentioning it now because if I do that, I want to at least have told you on the record. So it would be a good idea to have that memorized. It also just speeds things up dramatically if you have these conversions memorized. For torr, we could find on our yellow sheet that 1 atmosphere is equal to 760 torr. Two things that are equal makes a conversion factor. So 1 atmosphere on the top, that's what we want. 760 torr on the bottom, that's what we want to get rid of. And we get this number of atmospheres. So now we've got liters, we've got Kelvin, we've got atmospheres, we're finding moles. So we can plug in N equals pressure 1.16 dot 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 atmospheres times volume 0.224 liters divided by R with units of liters atmospheres per mole Kelvin, also divided by 328.15 Kelvin. On the bottom, the Kelvin's double on the bottom, the other Kelvin's only once on the bottom, those cancel. The atmospheres on the top cancels with the atmospheres on the bottom. The liters also cancels. The moles flips to the top. So N is 0.0096 dot dot dot, because I ran out of space, moles. Is that our answer? No, it's not our answer. It's one of the things we needed to get our answer. We're looking for molar mass, which is mass over moles. We have a mass, but it's in milligrams. The milli prefix means 10 to the minus 3. There's 1,000 milligrams in 1 gram. So it's 0.0388 grams. We take our grams, that's our mass, divide it by our moles, and we'll get the molar mass. What are the units for molar mass? Grams per mole. Nothing cancels, so it's grams per mole. 0.0388 divided by the number of moles we got. We get a value that's very close to 4 with 3 significant figures. Rounds up to 4, down to 4. Questions about any of the parts, the process? What gas do we have? Would be a fun bonus question that I could ask here.
Helium.
It's helium. Helium has a molar mass of 4 grams per mole, so this is probably helium. One for you to try. And we'll stop after this for lecture today. Okay, first thing we're going to want to do is write out all of our variables, or one of the first things that we want to do. We are told that the sample has a mass of 827 milligrams. Mass is lowercase m, 827 milligrams. We're also given a volume. The volume is 0.270 liters. Temperature is 88 degrees Celsius. Pressure, P, 976 millimeters mercury. Hopefully we all at least got there. It looked like everyone was at least writing their variables down, which is a great place to start. We also need to do some conversions. We're going to be using PV equals nRT, and We're going to be using R with units of liters atmospheres per mole Kelvin. So we need to do a couple of unit conversions. We already have liters, which matches the liters that's in our R value. We don't have atmospheres or Kelvin. We've got millimeters mercury and degrees Celsius. So we're going to divide by 760 millimeters mercury, multiply by 1 atmosphere. Millimeters mercury is the same as torr, so the conversion is the same. We're going to add 273.15 to our temperature. Should get 361.15 Kelvin. For the pressure, 1.28, and some other stuff after that. Atmospheres. What can we solve for? What do we need to solve for in PV equals nRT? We need to solve for N. So our first goal, find N, which is the number of moles. Now that we've converted everything, hopefully you've got all the tools that you need to do that. So give it a try. All right. We are finding N. There it is. N equals PV over RT. So our pressure, remember that I'm using the ... here just to save space. That means I am using this entire number. If you're using the dots, that means that you're doing that too. That's what it's supposed to mean at least. Plugging, plopping, putting all of our units in. Atmospheres cancel, liters cancel, Kelvin cancels, moles flips to the top. Number of moles is 0.011699865. Then we can solve for molar mass. Molar mass is mass, grams, wrong grams, weird grams. Okay, we got it. Over moles, which is units of moles. Our mass needs to be in grams. It's not in grams. We're going to divide it by 1,000.827 grams. So 0.827 grams divided by 0.01169 and some other stuff. Our units that we end up with are grams per mole. And the number we get is 70.68. That would round up 70.7 grams per mole. The fun bonus question, what's the identity of the gas? You might think that it's gallium, because gallium has a molar mass of 69.72. Gallium's not going to be a gas at 88 degrees Celsius. This is probably chlorine, because chlorine exists as Cl2. It's pretty close to that.